Good morning everyone and welcome to another lesson. In this video, I will be teaching you how to properly draw a diagram from a material balance problem and how do we perform the material balance calculations themselves. So let's get started. This PowerPoint presentation again has already been uploaded to your Blackboard accounts, so you can check it out later. Let's start with the concept of material balance. Material balance is a direct application of the law of conservation of mass to the design of processes. You already know what the law of conservation of mass is. It's simply saying that the mass going in a process should also be the mass going out of the process. So that's mass in equals mass out. If we want to take a look at the bigger picture, the material balance process is actually this whole equation. It's mathematically represented as inputs or in plus generation minus outputs or out minus consumption equals accumulation. The law of conservation of mass states that mass can neither be created nor destroyed in any physical or chemical process. For this general equation, there are some assumptions that would be helpful in our material balance. So let me first write this entire equation. That is input plus generation minus output minus consumption equals accumulation. Okay, for the classic material balance problems, we do have several types. We have steady state and unsteady state. For steady state material balances, what we mean is that there is no accumulation in the system. So for steady states, your accumulation is zero. There is no mass that is accumulating within the system. That means that your equation simplifies to just inputs plus generation minus output minus consumption equal to zero. If we are to rearrange this equation, you would get input plus generation equals output plus consumption. And if we further simplify this material balance, you can assume that it's a steady state process and it's also a material balance with no chemical reaction or without chemical reaction. If you don't have a chemical reaction occurring in your process, that means that you are not generating anything, you're also not consuming anything. So your material balance would only simplify to input equals output, which brings us to the main tenet of the law of conservation of mass. Okay, so for the first part of our discussion, or the first half of our term, we will be dealing with processes without chemical reactions. So this equation is the one that we will be using. Input equals output. Now, for unsteady states, this is the case wherein your accumulation is not equal to zero, or your accumulation has a constant value. If accumulation has a constant value, then you are already performing an unsteady state material balance, which we will not be discussing in this course. Okay, so we will just be focusing on the steady state processes. For unsteady state processes, you could also call this the batch processes or the semi-batch processes. So going back, okay, so this general mass balance equation, as I have discussed, the generation and consumption are associated with chemical reactions. We will only be using them if we are already dealing with chemical reactions, which will happen on the second half of our term. The accumulation results from an imbalance of inputs and outputs. So if one is bigger than the other, they will no longer be equal, so therefore you would have accumulation. Okay? We have several types of processes. This is what I have mentioned earlier. you can classify processes into three types. You have the batch, continuous, and semi-batch processes. The batch or the transient, or you can also call it the unsteady state, is where accumulation is constant. Okay, and the continuous or the steady state process is where accumulation is zero, so your input is equal to your output. The semi-batch is a gray area between the batch and continuous processes wherein you can combine both the concepts of batch and continuous processes. For now, we will be focusing on continuous processes or steady state processes. So let's get on with the main topic of this lesson: how to make a material balance. For me to be able to discuss to you how to perform a material balance, we would need to solve a sample problem. So for this instance, we have the steps on how to prepare a material balance, and we will also be solving a problem along the way. Okay, so here are the steps. We have four steps on how to perform a material balance, and we have here a sample problem. So this is our problem. An aqueous solution of sodium hydroxide contains 20% NaOH. It is desired to produce an 8% NaOH solution by diluting a stream of the 20% solution with a stream of pure water. Determine the feed rates of 20% solution and diluting water needed to produce 2,310 pounds mass per minute of the 8% solution. Okay, the first thing that you should know about is how to write a proper diagram that represents the problem. So let's revert back to our whiteboard. To write or to draw a proper diagram, you first need to know the basics. Well, the basics are, we have discussed this previously in our lesson on process and process variables. The first thing to know is we represent process units with boxes. In this case, the process is we are diluting one stream with water to make it more dilute. So the process here is called mixing. And if your process is mixing, then the process unit is called a mixer. So let's draw a box with the name of the process unit, mixer. Now you know that process units should have inputs and outputs. So it's now time to place inputs and outputs. Based on the problem, we have two inputs and we have one output. Your two inputs, first, is the original sodium hydroxide solution. Your second input would be your water, which would be used as the diluent to the solution. And your final stream is the output, which is the diluted sodium hydroxide solution. So that is how you write arrows pointing in and pointing out of the box to represent if they are inputs or outputs. So let's go back to the problem and see the values. Okay, so your original solution is an aqueous solution that is 20% sodium hydroxide. We want that to be diluted to 8% with or using water. Okay? And another given is that your final solution is 2,310 pounds mass per minute. So let's write that. Your initial solution, you first need to name your streams. In this case, you can name your streams whatever letter you want or whatever number you want. But in order to avoid confusion, I will be naming my streams as A, the original stream, B as the pure water stream, and then P as my product. You can use whatever letter you want as long as you don't get confused between those letters. Okay, so your stream A is 20% sodium hydroxide solution, and since this is aqueous, the remaining 80% or the balance would presumably be the solvent or the water. Your stream B is pure water, 100% water, and your product is only 8% sodium hydroxide. And since this is aqueous, the balance is 92%, that is your water. Another given is that P, or your product stream, has a value. and that is 2,310 pound mass per minute. And that is our entire diagram. For you to be able to solve a problem efficiently, you have to learn how to properly write a diagram. If you have some errors in writing in your diagram, then almost always you would also have errors in your final answer. So always check if you have the right diagram. Okay, let's go back to the problem and take a look at what are the required. Okay, by the way, let's go through these steps. So step number one is draw and label the process using block diagrams. We have done that. And label the given values with correct units. We have also done that. Also, do not forget to properly place your inputs and outputs. So the direction of the arrows here are very important. We are now on step number two. Select your basis based on the required data. And by the way, what are the required data? So based on the problem, we are required to determine the feed rates of stream A and stream B. So we are required to determine stream A and stream B as written here. Okay, next, step number two, choose your basis. Now we have already tackled choosing basis in our previous lessons. We want a basis that would simplify our calculations. If you take a look at our flowchart or our diagram, you can see that there is only one mass flow rate value, and that is for P. And if you would remember, if you're given a mass flow rate, a very good basis would be always the denominator. In this case, our denominator is minutes. Therefore, a very good basis would be 1 minute of operation. That means that if we section out 1 minute of the operation, we are sure that our product amount is 2,310 pounds. So let me write here, P is already 2,310 pounds mass. Okay, that is the effect of using a very good basis. Now, next step. Next step here, number three, select your system boundaries and perform material balances starting with the OMB, then follow with the individual balances of the components. Okay, now what is the OMB? The OMB stands for overall material balance. The overall material balance is simply your inputs is equal to outputs, and we will do that later. But first, let's select our system boundary. The system boundary is important because you can only consider a group of process units or a single process unit at a time, at any given time. So in this case, since we only have one process unit, you have actually no choice but to select the entire process unit as your system boundary. We select system boundaries simply by drawing a dashed line around the process units that we are considering. The importance of this system diagram is for us to know which area to consider. So if you have written your system diagram, just know that you will only be considering the streams coming in and coming out of that boundary. Okay? After that, we can now perform the overall material balance. The overall material balance is performed by simply taking every stream that is going in and equating that. The overall material balance is simply done by listing every stream that's going in and equating that to every stream that's going out. So it goes like this. The OMB for this process is A, which is coming in, plus B, which is also coming in, is equal to P, the only stream that is coming out. As you see here, the use of letters as representations of the streams come very handy here because we can easily represent them in an OMB. It would be very difficult for you to perform an OMB if you are using words or phrases to represent the streams. That would be very tedious for you to write. Okay? Now that we have our OMB, Next step is to perform the balances of each component. Or before that, if you take a look at our overall material balance, if you take a look at the variables, A and B still does not have any value because those are our required, while the variable P already has a value, and that is 2310. So you can already substitute in this equation. A plus B equals 2310. Of course, it's already understood that the units of this equation are in pounds. Okay? The next step is to perform component balances. Component balances are performed for every component of a system. If you take a look at our diagram, we only have two components, that is the sodium hydroxide and the water. So the number of components you have is also the number of possible component balances you can have. And in terms of component balances, it's always easier to first perform your component balance for the tie component. So what is a tie component? We define a tie component as a substance that goes in and goes out of the process in just one stream. One stream going in and one stream going out. If you take a look at our process, if you consider our two components, let's first start with water. For water, it goes in at streams A and at stream B, and it goes out at stream P. So therefore, we can say that water is not a tie component because it goes in through two streams and comes out through one stream. Okay? If you take a look at sodium hydroxide, it goes in through stream A and it exits through stream P. So it satisfies the criteria of a tie component because it goes in through one stream and it goes out through one stream. So we can write here that our tie component is sodium hydroxide. It's important for you to determine the tie component to lessen the complexity of a material balance problem because it's always the easiest to perform the tie component balance first. Okay, so let's proceed with the component balance. You simply write NaOH balance. Now, for the OMB, we perform the material balance for the entire stream. For the NaOH balance, we will only be performing the law of conservation of mass for sodium hydroxide. So how do we do that? By the way, if you go back to our diagram, it was not specified if the 20% NaOH is percent by mass, percent by mole, or what. But based on our previous video, I have mentioned that if it's a liquid and if there's no mention, then this is automatically percent by mass. Okay, so if that's percent by mass, how do you get the amount of sodium hydroxide in stream A? It's easy as multiplying the percent by mass with the total amount of the stream. If the total amount of the stream is A, of course, we don't know yet what's the value of A. So therefore, the amount of sodium hydroxide in stream A is simply 0.2 or 20% multiplied by the total or A. So 0.2A means that you have 20% of sodium hydroxide in A. Okay? And that should be equal to 8% of the output stream P, 0.08 P. That is your complete sodium hydroxide balance. Because sodium hydroxide is only involved in two streams, you should only have two terms in your material balance equation. Okay? Now, to simplify further, we can already substitute the value of P because there's a given, that's 2,310 pounds. So therefore, 0.2A is equal to 0.08 times 2,310. And as you can see, we can already solve for the value of A. So let's compute. So this is 2310 times 0.08 divided by 0.2. So A is 924 pounds mass. Sorry, let me move Okay, we have already determined the value of A or the mass of A. Now, since this is a steady state problem and your basis is 1 minute, your answer in A could be 924 pounds mass, or if you want to be more proper, you can write it as 924 pounds mass per minute because we have already set the basis as 1 minute. Okay, so we already have a value of A. We only need to get the value of B. You can do this using two things. The first thing is you can go back to the overall material balance or the OMB. Since we already have a value of A, you can substitute that there and you can solve for the value of B. So let's do that. So if we rearrange this, B becomes 2310 minus A, which is 924. We simply solve B as 1,386 pounds mass per minute. So that's the easy part of material balance. If you already have one of the values, you can substitute to the overall material balance and get the remaining values. Okay, that's one of your options. Your other option is to perform the water balance because remember we have two components, the sodium hydroxide and the water. Therefore, you can perform two component balances. We have already performed the first, so let's try to do the second as a way of checking. Okay, so let me write it here in this part. So let's perform a water balance. This is our second component balance. For the water balance, we will proceed exactly as how we did proceed with the sodium hydroxide. So collect everything that's going in and equate that to uh, and equate that to that and equate that to the stream going out. Okay. So for A, we have 80% water, so that is 0.8 A plus we also have water coming from stream B, and in fact, stream B is pure water. So we simply write B, point A plus B equals 0.92 P because stream P is 92% water. You already know the value of A, so that's 0.8 times 924. We are solving for B. Remember, we wanted to check if we would arrive with the same answer and substitute the value of P, that is 2310. If you solve the value of B, that would be 2310 times 0.92 minus 80% of 924. Okay. We arrive with 1,386 pounds mass per minute, which is the exact same answer we obtained using the overall material balance or the OMB. You see here, it does not matter if you go back to the OMB or if you try another method. If your answer is correct, every equation should be correct as well. So thus, we have performed a full material balance on a problem. You have to get acquainted with this process because you will be doing this for the rest of the term. Okay? Now for the rest of the video, we will be doing more examples, and at the end of this video, you would be given a problem set. Okay, let's proceed with more examples. This one. We have 1,000 kilograms per hour of a mixture of benzene and toluene containing 50% benzene by mass is separated by distillation into two fractions. The mass flow rate of benzene in the top stream is 450 kilograms benzene per hour, and that of toluene in the bottom stream is 475 kilograms toluene per hour. The operation is steady state. What are the distillates and bottoms flow rates? Okay, let's draw the diagram. For distillation, one thing that you have to remember is it's always one stream going in and it's multiple streams coming out. In this case, it's a simple distillation wherein you only have one distillates and 1 bottoms fraction. So if we draw that, I would call this my distillation tower. Remember, it's a process unit. Your feed comes in. You can represent feed as F or whatever letter you want. And I would be representing the top product or the distillate with D and the bottom product with B. So as mentioned, our feed contains an equimolar mixture that's 50, sorry, let's check. You have 1,000 kilograms per hour. Okay, that's not percent by mole, it's 50% benzene by mass. So you have 50% by weight, benzene. Let's represent benzene by Bz. And 50% by weight, toluene. And the flow rate of the feed is 1,000 kilograms per hour. Okay. Your distillate contains 450 kilograms per hour benzene. Take note that it did not mention that the entire flow rate of the distillate is 450. It simply mentioned that benzene flows at 450 kilograms per hour. Okay, so it's important to make that distinction. And then in the bottoms product, we have a given of 475 kilograms per hour of toluene. So this is all of our given. If we follow the steps that we laid out on the previous problem, after you have written or after you have drawn your flowchart or your diagram, you then set your boundary or your system boundary. In this case, again, we are considering a single unit process, so our boundary is simply the entire distillation tower. That is our boundary. Next, set your basis. What could be a very good basis here? So this is a steady state process. You're given the value of F, which is a mass flow rate, and the denominator is hours. So a very good basis here is 1 hour of the operation. In that way, you already know that the value of F is 1,000 kilograms, and that would aid us in our material balance. Okay, so let's proceed. We then proceed with our OMB, or our overall material balance, wherein we collect all of the streams. So what is your OMB here? You only have one stream going in, that's F. You have two streams going out. So we write that as F equals distillate plus bottoms. It's always everything that's going in equals everything that's going out. Okay? Now we have a value for F, that's 1,000. So let's substitute 1,000 equals distillate plus bottoms. And we have already performed our OMB. So we're done with our OMB. Okay? Next, since we have two unknowns, remember your unknowns are the distillate and the bottoms, we need to have two equations to solve for two unknowns. So what other equation could you think that we can use here? Of course, we will be using the component balances. For the component balances, we can consider two components, your benzene and your toluene. The problem is, unlike the previous problem, we don't have a tie component here. Remember, the tie component enters in one stream and also exits in exactly one stream. In this case, both benzene and toluene enters in one stream and exits in both streams, because what the problem did not tell you is that there is still some residual toluene in the distillate, and there is also some residual benzene in the bottoms. Because this distillation is not 100% perfect, it was not able to separate these two substances perfectly. Okay, so we have to figure out how much toluene is in the distillate and how much benzene is in the bottoms product. So that represents another unknown. So I will be representing the amount of toluene in the distillate as X and the amount of benzene in the bottoms as Y. So total, we now have four variables: B, or the distillates, B, or the bottoms, and we also have X and Y. So mathematics states that we have four unknowns, therefore we should also have four equations. And we already have our first equation in the simplified OMB. To get the remaining equations, what can we do? So before we go to our component balance, we first use our common sense and take a look at the distillates. So if you take a look at the distillates, you only have two components there, that's the benzene and the toluene. Therefore, logic would state that if you add the amount of benzene to the amount of toluene, then you should be able to arrive with the amount of distillates. In terms of mathematical variables, we represent that as 450, which is the amount of benzene, plus X, which is the amount of toluene, is equal to D, or the total distillates. That is another equation. So we do the same thing with the bottoms. We say that 475, or the total amount of toluene in the bottoms, plus Y, or the amount of benzene in the bottoms, is equal to B, the total amount of the bottoms products. And we now have our third equation. We only need one more equation to solve the problem. So what is that equation? That equation is your component balance. You choose between the benzene balance or the toluene balance. So let's go with the benzene balance. It doesn't matter if you choose benzene or toluene in this case because you would arrive with the same answer. So if we choose to balance benzene in our component balance, later on during checking, you can then use the toluene balance as a way of checking. Okay, so how do you write the benzene balance? The benzene coming in is 50% of the feed, or zero point 0.5 of F, and that is equal to how much benzene is in the distillates. That's already given. That's 450 kilograms. Plus how much benzene is in the bottoms. So in the bottoms products, we have represented the amount of benzene as Y. So we now have our fourth equation. And if you take a look at the fourth equation, it's very easy to solve and we can already obtain the value of Y because we already have the value of F, which is 1000. So this is zero point 0.5 times 1000 equals 450 plus Y. Solving that, we get this is 500 minus 450, so your Y is 50. Therefore, we interpret this as the bottoms product having 50 kilograms of benzene in the bottoms product. So we now have the value of Y. Okay, now that you have the value of Y, what can you do next? Take a look at your equations. Where can you substitute the value of Y? If you take a look at equation 3, if you substitute the value of Y, you can get the value of B. So in equation 3, we say 475 plus Y is equal to B. So 475 plus 50 equals B. Therefore, B is equal to 525 kilograms. Or to be more specific, since your basis is 1 hour, this is for 525 kilograms per hour. We now have the value of B because that is one of, sorry, I forgot to write the required. We are required to find out the values of D and B. So we have already found out the value of B, and that is 525 kilograms per hour. So what can you do after this? In what equation can you substitute B? You have two choices. You can go to equation number, sorry, you cannot use equation number 2 because we don't have a value of X in the meantime. So what we can do here is you substitute the value of B in equation 1, and it's just simple subtraction. So therefore, 1000 is equal to D plus 525. We have a value of D, sorry, it's not seen. We have a value of D, which is 475 kilograms per hour. And you're finished with the entire material balance. So you see, the problem becomes easy if you know how to write a proper diagram, and if you know how to perform an OMB, and if you know how to write the component balances. It would also need your knowledge of mathematics, even linear algebra, because sometimes you need to solve several equations simultaneously, like two equations, two unknowns, three equations, three unknowns simultaneously, etc. Okay? If you have questions, again, you can reach me every Sunday through Zoom meetings. Okay, so let's proceed. The last two problems will be given to you as a problem set as a way for you to practice. But I will be helping you since I will be laying out the initial solution and I will let you figure the rest of the solution to your own. Okay, next problem. So let's transfer here. Next example. The oxygen in air is usually sufficient to sustain combustion, but it can be enriched to make combustion more efficient. In a certain process, it is required to produce a 50-50 mixture of oxygen and nitrogen by mixing air and pure industrial oxygen. How much, in kilomoles per day, of the 50-50 mixture can be produced from 250 cubic meters per day of pure oxygen at STP, or standard temperature and pressure? So I will help you construct the diagram here. So you will be labeling this number one in your problem set. Our unit process here again is a mixer because we are simply mixing air with pure oxygen. So your first stream is your air. I will be labeling this as A. This is air. And of course, air contains two components. That is 21% oxygen and 79% nitrogen. Now remember, we are dealing with gases here, so it's assumed that this percentage are in percent by mole. So everything here is in percent by mole. Okay? And the problem also states that we want to mix that with pure oxygen. So stream B is pure oxygen, or 100% oxygen. In order for us to arrive with the product, let me go back to the problem. The product is a 50-50 mixture, or a 50% oxygen, 50% nitrogen mixture. So let's write 50% oxygen and 50% nitrogen. Again, these are all in percent by mole because we're dealing with gases. And the problem is asking how much of the 50-50 mixture, so the required is how much of stream P can you make coming from a value of B, which is 250 kilomoles per day. Let's verify. Sorry, that's 250 cubic meters per day of pure oxygen at STP. Okay. The required value of P should have the units of kilomoles per day. That's our entire problem. And of course, the first step is to determine our system boundaries. Well, you now know that our system boundary is simply the entire mixer. So let's write a dashed line for that. You have two input streams and you have one output stream. And we are required to determine the value of the one output stream. Okay, let's start with the basis. As you have sensed the pattern for this, we are generally taking a look at what's the given if it's a flow rate, and we take a look at the denominator and we usually use that as our basis for easier calculations. In this case, B has a value of 250 cubic meters per day. The denominator is day, therefore a sensible basis is to use 1 day operation. That gives us a value of B that is 250 cubic meters oxygen at STP. Now we are dealing with gases. So one thing that you have learned in your general chemistry is if you're dealing with gases, you have a way on how to convert from volume to mole to mass. In this case, since your required is in kilomoles per day, you need to convert the cubic meters to kilomoles. How do you do that? You simply use the ideal gas law. PV equals nRT. You are given the pressure and the temperature because that is in STP. In or under STP, the standard temperature is 0 degrees Celsius and the standard pressure is 1 atmosphere. And I will leave this to you to convert from cubic meters to kilomoles. And once you have done that, you can now perform your OMB. So what is our OMB here? In the previous problems, we have been performing OMB with mass or with kilograms with pounds. In this case, since there's no chemical reaction, it's also safe to perform the OMB using moles. But keep in mind that you can only perform OMB with moles if there is no chemical reaction because the number of moles is conserved between the reactants and the products. Okay, so the layout of our OMB here is A plus B is equal to P. Okay, and after this, you simply have to substitute your given here, and then you can perform the component balance. You have two components here. You have the oxygen and the nitrogen. So you should be able to perform two component balances for this problem. However, you only need one component balance to fully solve the problem. The other component balance would be useful for checking if your answer is correct. Okay, so I have laid out the solution. You continue this in your problem set. So this is number 1. Next problem. Okay, this is the last problem, and this would be number 2 in your problem set. An experiment on the growth rate of certain organisms require an environment of humid air enriched in oxygen. 3 input streams are fed into an evaporation chamber to produce an output stream with the desired composition. A. Liquid water fed at a rate of 20 cubic centimeters per minute. B. Air, which is 21% oxygen and 79% nitrogen. And C. Pure oxygen with the molar flow rate 1/5 of the molar flow rate of stream B. The output gas is analyzed and is found to contain 1.5 mole% water. Draw and label the flowchart of the process and calculate all the unknown stream variables. So let's write the given. We have another case here of a mixer because you are simply mixing 3 streams in order for them to achieve the parameters of the output stream. So in your problem set, kindly label this as number 2. So our 3 input streams are A, B, and C. A, B, and C. And we only have one output stream. I will be calling that P. Now, if you take a look at the given again, stream A is liquid water at a rate of 20 cubic centimeters per minute. So A is 20 cubic centimeters per minute. This carries pure liquid water. B is air. So this is 21% oxygen and 79% nitrogen. Keep in mind that these are percent by mole values because they are gaseous. And then C is pure oxygen. And it was stated that the flow rate of C is 1/5 the molar flow rate of stream B. So therefore, we can write a relationship wherein C is equal to 1/5 of B. So that is your entire diagram. We want these streams to mix such that your stream P contains 1.5 mole percent water. And by deduction, you now know that stream P would contain three components. That's water, oxygen, and nitrogen, because you're mixing the three components. You're mixing the three streams containing those three components. Okay, so for the solution here, again, you define the system boundary. Since you only have one unit process, that is already your system boundary. Next, define your basis. We are only given one value here for the flow rate, and that is the flow rate of stream A. That's 20 cubic centimeters per minute. Therefore, a sensible basis for this would be 1 minute of operation. After that, we now know that the value of A is 20 cubic centimeters. Since this is liquid water, you know that the density of liquid water is about 1 gram per ml, or 1 gram per cubic centimeter. You can also say that your stream A is 20 grams of water. So that is everything that we know. Next part, you perform the OMB. So the OMB here would be the summation of all of the streams going in, A plus B plus C, equal to the stream going out, which is P. Now, depending on how you choose to tackle this problem, your OMB could be either in the basis of mass, if you want that, or your OMB could also be on the basis of moles. For my suggestion to you, it would be simpler if you proceed with moles. You simply have to convert A to moles, because everything else is in percent by mole. So it would be easier if your analysis is in moles. Okay, so that is already your OMB. And from your OMB, we can have simplifying assumptions such that C is equal to the 1/5 of B. So you can substitute that in order for you to lessen the number of variables. And then after the OMB, you perform the component balances. We have three components. So therefore, you can perform three component balances, but in this case, you will only be needing two component balances, or maybe just even one. So you would have to check. Okay? So you have to submit you write your solutions, your full solutions for problems 1 and 2. You write them in clean sheets of paper. After you're done, kindly take a picture of that and then compile them to a single PDF file and then upload it to problem set number 1 under week 1. Okay, with that, that ends our lesson. I will see you next week, and as always, keep safe.